Hi everybody, welcome to this lesson on latent heat and changes of state. So what we have here is a picture of a girl, and what happened with this girl is she just got out of the pool, probably has a little bit of water on her surface, and what's going on is this layer of water on her surface, this liquid water, as the wind blows across her, this liquid water is going to form water vapor. Now, this is vaporization, and you know that in order to do so, to go from the liquid to the water vapor, we need energy. So what happens is this energy comes from the girl. So she's going to be losing thermal energy, which goes into the water to vaporize it. And as a result, she's going to feel cool. Another situation similar to this is this boy over here. Now this boy is eating a popsicle. Popsicle is made up of a solid. So here's a little solid. And what's going on in this situation is we want to take the solid and it's going to be changed into a liquid. So it's going to be melting inside of his body, maybe even inside of his mouth. So in order to do this, we have to break the bonds between the particles of the solid. And what happens is we're going to be absorbing energy from the boy. So the energy is going to go from the boy to the solid ice, changing it into water. And as a result, the boy's body is going to cool off. It's going to lose a little bit of energy. Now, in this picture, what we have is we've got some condensation. So the reason we have condensation is we've got water vapor that's in the air. And when it encounters a cold surface, such as the one we have here, it changes into liquid water. So we've got some liquid water here. Now, in order to do this, it's not going to happen on its own. We have to take energy away from the water vapor. So the energy from the water vapor has to go somewhere. In this case, it's going to go to the environment. Probably goes to the pop can. That's a very little, small amount of energy, so you really don't notice a big temperature change here. But nonetheless, we have to take that energy away. Now, in the last picture, it's an interesting picture, popsicles on top of Florida oranges. Well, what happens here is when there's a risk of frost, orange groves in Florida, farmers there are going to spray them with water. And what happens is the liquid water, when it's cold enough that you spray on the oranges, changes into a solid. But in order to do this, you have to take energy away. So what happens is energy is released into the environment and is actually going towards the oranges. So what happens is the oranges do not freeze, and in fact they're warmed up a little bit. Not a significant amount, but it's enough to prevent the oranges from becoming damaged as a result. So what happens is we've got these changes of state. Some of them, such as melting, vaporization, require energy from the environment, the input of energy. Others, such as condensation and freezing, require energy being released into the environment. So the energy has to go somewhere. That's the one we typically have a hard time with. But think about a fridge. We're freezing something, say a freezer. We're taking energy away from the object and it's going into the environment. So that's why the back of a freezer is often warm. You're taking the energy away from the food inside and releasing it into the room. So just to kind of recap our learning goals today, we're going to be looking at heat of fusion, so latent heat of fusion and vaporization. We'll talk about application of latent heat and changes of state, such as popsicles, evaporation of water, steam burns, and things like that. And then we're going to be doing heating and cooling curves, which we'll be discussing in a moment. And we're doing some calculations with these particular changes of state. So what I have here is just the same diagram we had prior, where I've added in just some of the applications. So what I have here is the popsicle. It's absorbing energy from the body, and the energy is going towards the solid, breaking those bonds over here. And what happens is when we're vaporizing, the energy, again, is being absorbed from the environment to the liquid, allowing it to form the gas in vaporization. And over here in condensation, we have to take energy away. An example of this would be water that's condensing on a particular surface. It might be your hand. And what happens is the energy that's released to your hand can cause a nasty steam burn. So that's all the energy that's being released from the particles as the particles or the substance changes from a gas to a liquid. And again, oranges, same thing happens with oranges. As the liquid changes to a solid, we have a release of energy into the environment that's absorbed by the oranges then, as a result, protecting them. So, why is thermal energy required? Well, it has to be added or removed to basically break or form bonds between molecules. Let's take a look at a couple of examples. What I have here is one of the links we have on our website. And you can see here we've got a solid. And all of these particles are really attracted to each other. So what that means is there is some kind of attractive energy or potential energy associated with these particles. Let me show you this. So I've got here two atoms, and you can see that if I bring them too close together, there's a lot of repulsion happening here. There's a lot of potential energy. You can see it up here. And what happens is if I bring them too close together, that potential energy causes the particles to move away from each other. Similarly, if I move this atom out a little bit, there's attractive force between these two atoms that will slowly bring them back together again. So we've got this potential energy, the energy because of these bonds. And what happens is, when I've got this potential energy, this bond energy, to change this substance into a liquid, what I have to do is I have to add energy. This energy initially is going to cause the particles to vibrate faster, giving them a little bit of EK, and then eventually some of these particles are going to break free and start floating around. So we've got a liquid here. And some of them, in fact, are actually forming a gas. So we're breaking these bonds. So thermal energy can be used to break the bonds to cause melting and vaporization. And you're increasing the potential energy between molecules. Because what happens is, as the molecules move further apart, they want to come back together again. So we have a lot of potential energy as a result. Now, once I take energy away from these particles and they slow down, they'll have less EK, they gradually get closer together, and that potential energy we had, decreases. So when you're taking energy away, you're going to be forming those bonds, and you can have freezing or condensation occur as a result. And let me just show you a couple of examples again on that. Let's look at water. Now, water is a little bit unusual just because there are attractive forces between the water molecules. So you can really see them here. The water molecule has a positive end, hydrogen, and a slightly negative end, the oxygen. And the two opposite charges attract each other. So if I wanted to break these bonds between the particles, again, I have to add energy. This energy is going to cause the particles to move. And you see them here, I've broken some of these bonds. So the particles are not being held together as tightly, and we have a liquid now. If I keep adding more energy, I'll be further breaking the bonds. And eventually what's going to happen is these particles are going to form a gas. There's very little attraction between them. Now, if I want to, and there's a lot of potential energy here. These particles want to come back together again, and eventually they will. So if I reduce the kinetic energy of the particles, you can see that the potential energy allows them to come together, the attractive forces, and the potential energy now is decreasing as the particles get closer. As close as they can get, there's no further attraction possible between them. So you get the idea here in terms of bonds and what's happening with bonds. That's key in this particular set of changes of state. Now, when you look up here, the amount of energy that's required to melt or freeze an object, so if you're adding a certain amount of energy, the amount that's required to completely melt 1 kilogram of the substance is called the latent heat of fusion. And for water, it's around 340,000 joules per kilogram. And if I'm freezing something, I have to take that much energy away from the object, from the molecules, in order to freeze it. Now we also have on this side LV, latent heat of vaporization, and that's the amount of energy it takes to completely vaporize a kilogram of something. So in case of water, I believe it's about 2,300,000 joules per kilogram. And if I want to condense something, that's how much energy I must be removing. So again, use LF, melting and freezing, and LV for vaporization and condensation. You can look these values up on page 291 of your textbook. They're basically properties, fundamental physical properties of a substance. And the equations we can use to determine the amount of energy required to have a change of state occur is this. E thermal equals ML. Could be E thermal equals MLF or E thermal equals MLV. So that's how we can determine the amount of energy. And the best way to look at this is an example. So what we have here, we've got lead that has a mass of 652 grams, and it has a latent heat of fusion of 2.5 times 10 to the 4 joules per kilogram, from page 291. And what's going on here is we want to change the molten lead to a solid piece of lead. So what has to happen is we're going to go from a liquid to a solid. In order to do that, we have to remove thermal energy. So we're going to calculate how much thermal energy must be removed in order to do this. So we've got our equation. We're using LF fusion, latent heat of fusion, because we're going from a liquid to a solid. I plugged the values in, so I've got my mass. There's the latent heat of fusion for 1 kilogram. I only have 0.652. So I end up with 16,625 joules. So with two significant digits, we have 17,000 joules of thermal energy that has to be removed from the lead, molten lead, to allow it to solidify to form a solid. So it's a very simple calculation that we have here. Now the other thing we can do is we can draw a graph of the temperature of a substance as it's undergoing changes of state. So what I have here is a heating curve, we call it, because we're heating something up. So it's a heating curve for water. And the water is in the form of a solid. So it's ice at the beginning at minus 10 degrees. And we're going to be heating it all the way to 110 degrees, where it's going to be steam. So we've got a vapor. Now, you'll notice that as we increase temperature, as we go with time, we're continually heating this on a hot plate. So what happened was we had a hot plate, we had a container that had ice in it. So there's my ice, and we're continually adding thermal energy. And as we're adding thermal energy, what happens is initially the thermal energy goes into EK, temperature. The particles are vibrating faster as represented by the increase in temperature. However, all of a sudden we have this plateau. So what's happening here? Well, remember, we're going from a solid to a liquid. So what's going on here is we're breaking the bonds. We're breaking the bonds between the water, solid water molecules. Okay, sorry about that. My battery just died. Now, once the bonds are broken, the particles are moving around, and then what happens is they increase their kinetic energy up until we hit 100 degrees. And at that point, we're going to have the liquid changing into a vapor. So we're going to have vaporization. So again, we're breaking the bonds, and while we're breaking the bonds, you notice that the temperature stays constant. All the thermal energy that we're using, we're adding to the substance, is being used to increase the potential energy. We're breaking the bonds, and that separates the particles, giving them more potential energy. Once the bonds are all broken, the particles are moving around again on their own, and the thermal energy is used to increase the kinetic energy associated with the particles. So we have over here. So what the temperature increase, what happened? The thermal energy went into EK when the temperature increases. When the temperature stays constant during a change of state, and this is really important, so during any change of state, the temperature is constant. What's going on here is we're using a thermal energy to break bonds, the bonds between the particles. And as a result, the particles want to get back together again. In other words, they've got more and more and more potential energy. So what's going on is the following, just as a recap. So remember, we're continuously adding thermal energy. So over here, when we have a solid, as I'm adding thermal energy, the energy is being used to increase the movement of the particles. There's more and more EK. Once I hit the melting point, that energy is no longer going towards EK. Now it's going towards the potential energy of the particles being forced apart, giving them more potential energy. And so we're really breaking bonds with that energy. Once we've broken all the bonds, the particles start moving again, so they've got more EK until we hit the vaporization point. At that point, again, just like before, the bonds between particles are broken, increasing the potential energy until we have a change of state. Everything is in a vapor, and then the energy is being used to increase the EK. So basically, it's something like this. I'll show you a quick video clip. Okay.
We prepared a graph representing water to show energy changes, kinetic and potential, with temperature. We'll start with the solid phase, using ice as our solid. When water freezes, it forms a three-dimensional structure that prevents the water molecules from getting too close to one another. Each oxygen atom is associated with 4 hydrogen atoms, 2 by covalent bonds, 2 by intermolecular forces. The covalent bonds are shown by the solid lines, and the intermolecular forces by the dotted lines. Intermolecular forces are unusually strong in water due to hydrogen bonding. The energy required to overcome these strong attractions is evident in water's relatively high melting and boiling points. For example, methane, made of molecules of similar size and mass, has a melting point of minus 183 degrees Celsius and a boiling point of minus 161 degrees Celsius. The steady addition of heat to frozen water causes the molecules to vibrate more, which raises their average kinetic energy. The kinetic energy of water molecules in an ice crystal is the result of the vibrational motion of the whole molecule as well as the vibrations of the hydrogen and oxygen atoms within each water molecule.
So that's occurring in this particular segment of the heating curve. Again, we're increasing EK, or temperature, of the particles. They're moving more.
As we continue to add thermal energy, the motion of the molecules becomes progressively more vigorous, and the temperature rises accordingly. At the melting point, 0 degrees Celsius, the intermolecular forces are no longer strong enough to withstand the violence. The continued application of thermal energy is now used to overcome the forces that lock the ice molecules together into a solid. As a result, potential energy increases. This increase in potential energy causes a phase change from solid to liquid. Notice that the temperature of the substance does not rise during the melting, since the added thermal energy is converted to potential energy. The energy absorbed to melt 1 mole of ice is called the molar heat of fusion,
which we call the latent heat of fusion in physics. So now where we are is at this point here. So what's happened is we've taken the molecules, separated them a little bit, and they've gained a little bit of potential energy. Let's see what happens when we continue applying heat.
of fusion. Let's now examine the energy changes in the liquid phase. Once all the solid is melted, the further addition of heat causes the average kinetic energy to increase again. The molecule's vibrational motion, as well as translational motion and rotational motion, increases. We measure these increases in kinetic energies as an increase in temperature. At the boiling point, 100 degrees Celsius, the temperature does not rise, so we know that the average kinetic energy holds constant. Now the added energy works against the intermolecular forces, which hold the molecules together in the liquid. The molecules then separate, storing the added energy as potential energy. Free of these intermolecular forces, the molecules fly apart as a gas. Once again, since the temperature of the substance does not rise during melting, the added heat increases the potential energy of the molecules. A phase change has occurred, liquid to gas. The energy absorbed per mole of water during boiling is called molar heat of vaporization,
which we call latent heat of vaporization.
After the phase change of water liquid to water vapor, the temperature rises again, as the added heat increases the average kinetic energy of the gaseous molecule. plateau at the boiling point is longer than the plateau at the melting point because it takes almost 7 times more energy to vaporize liquid water than to melt the ice.
Okay, so that's for a heating curve. Now, if we have a cooling curve, what's happening is I'm taking energy away from the substance, and what's going on is going to be reducing the motion of the particles in the gas until they get to the point where the particles are going to start reforming some of those bonds. The bonds are forming. The potential energy as a result decreases because the particles are closer together, and we end up with a liquid. Once we have the liquid, the further removal of energy causes the EK to decrease until we get to the freezing point. And again, at that point, at the freezing point, the particles get closer together, and we have further reduction in the potential energy between the particles until we have a solid. And at the solid, the particles, removal of energy results in the further reduction in motion of the EK. So basically, it's a mirror image of the heating curve. We call it a cooling curve. In this course, we're going to focus on the heating curve. Okay, the important thing to recognize here is that during the change in state, the kinetic energy does not change, which means that the temperature of the object does not change, whether you're heating or cooling. All that changes during change in state is the potential energy. In the next segment, we'll look at how we can calculate these different amounts of energy that are required to be added or removed to cause these changes of state.